You know what's absolutely mind-blowing? Everything you see when you look up at the night sky, every star, every planet, every swirling galaxy, is made of the exact same stuff as you and me. The same fundamental particles that make up your coffee mug are out there forming stars billions of light years away. And that's where our cosmic journey really begins, with the smallest things in existence. I know it seems weird to start a conversation about astrophysics, the study of massive, distant objects, by talking about things so tiny we can't even see them with a microscope. But here's the beautiful truth. Understand these tiny particles, and you're one giant leap closer to understanding the entire cosmos. Now, I should mention that the universe is full of mysteries. There's dark matter, dark energy, and all sorts of strange phenomena that might require entirely new physics to explain. But today, let's focus on the particles we do understand, the familiar building blocks that make up what we call ordinary matter. You've probably heard of them before: protons, neutrons, and electrons. These three particles are the backbone of almost everything in the universe. But particles by themselves are just, well, particles. The magic happens when they combine into atoms. An atom is the smallest unit of regular matter. Think of it as the fundamental Lego brick of reality. And different atoms are just different combinations of protons, neutrons, and electrons stacked together in specific ways. Let's start simple with hydrogen, the most abundant element in the universe. A hydrogen atom has one proton in its nucleus, usually one neutron hanging out with it, and one electron orbiting around the outside. The proton has a positive charge, the electron has a negative charge, and they balance each other out perfectly. The neutron? It's neutral, no charge at all, so the whole atom has a net charge of 0. Now things get more interesting when you add more particles. Helium has 2 protons and 2 neutrons in its nucleus, with 2 electrons orbiting. Carbon has 6 protons, usually 6 neutrons, and 6 electrons, and you can keep building up from there. Here's a crucial concept. The number of protons in an atom's nucleus, that's called the atomic number, is what defines which element it is. Hydrogen will always have 1 proton. Carbon will always have 6. Change the number of protons, and boom, you've got a completely different element. But here's where it gets flexible. Atoms can gain or lose electrons through a process called ionization. They can also gain or lose neutrons, creating what we call isotopes, different versions of the same element. But change the number of protons, you've literally transformed one element into another. It's like cosmic alchemy. Now, I'll be honest, the way I'm describing atoms, with electrons orbiting the nucleus like tiny planets around a sun, is what physicists call the classical model. The real structure involves quantum mechanics and probability clouds and gets pretty wild. But this simple model works beautifully for understanding how chemistry operates, and that's what matters for our purposes. So we've got 118 different elements, each defined by a unique number of protons, from hydrogen at number 1 all the way up to oganesson at 118. The periodic table organizes all these elements by atomic number and groups them by their properties. Most atoms are stable. A chunk of iron will stay a chunk of iron. But atoms can bond together to create something entirely new: molecules. Take water, for instance. Water is 2 hydrogen atoms bonded to 1 oxygen atom, H2O. The oxygen atom sits in the middle with its 8 protons, 8 neutrons, and 8 electrons arranged in energy levels. The 2 hydrogen atoms attach to it, each bringing their single proton and single electron to the party. Together, they form this completely new substance with properties totally different from hydrogen or oxygen alone. And here's the cool part. Even though they're bonded together, the hydrogen and oxygen atoms keep their individual identities. Split the water molecule apart, and you get hydrogen and oxygen back. Under normal conditions, like here on Earth's surface, the rules of chemistry are pretty consistent. Elements maintain their form. But out in space, The universe has some seriously weird environments where the normal rules don't always apply. Like the interiors of white dwarf stars. Those are about as strange as it gets. Now, if you thought protons and electrons were small, hold on to your hat. These particles can actually be broken down even further into what we call elementary or fundamental particles. Particles that can't be subdivided anymore. Electrons are actually already fundamental, but protons and neutrons. They're made of even tinier things called quarks. Physicists have developed something called the Standard Model of Particle Physics to organize all these fundamental particles into two categories, fermions and bosons. The categorization is based on quantum mechanics and a property called spin. I won't dive too deep into the quantum weeds, but just know that all these tiny particles combine in various ways to eventually form the familiar particles we've been talking about. Protons, neutrons, electrons, and everything built from them. And speaking of fundamental particles, let me introduce you to one of my favorites, the photon. When you look up at a star and see it shining, you're seeing photons, tiny bundles of electromagnetic energy streaming across space. Photons are fascinating because they have no electric charge and essentially no mass, yet they're incredibly powerful. Think of them as little packets of pure energy. Here's what makes photons special. They're fundamental particles called bosons, and they always travel at the maximum speed possible in the universe, the speed of light. That's 186,000 miles per second or 300,000 kilometers per second. Always. No exceptions. Photons carry all forms of electromagnetic radiation, not just the visible light we see, but also radio waves, X-rays, everything across the spectrum. And like other fundamental particles, photons behave as both waves and particles at the same time, which is wonderfully weird. When you think of photons as waves, they have a wavelength. And here's the key relationship. The shorter the wavelength, the more energy that photon carries. This is crucial for astrophysics because different cosmic objects emit photons at different wavelengths, and by detecting those photons, we can learn what those distant objects are made of, how hot they are, how fast they're moving, all from light that's traveled across unimaginable distances to reach us. So here we are, starting with the absolute tiniest things in existence, quarks and electrons and photons, and building our way up to atoms and molecules. And from there? Well, from there, we build stars. We build planets. We build galaxies. We build the entire observable universe. And we build us. That's the incredible thing about studying these particles. We're not just learning about abstract physics. We're learning about our own origin story, written in the language of protons, neutrons, and electrons. Every atom in your body was forged in the heart of a dying star, scattered across space and eventually assembled into you. From the smallest particles to the largest structures in the cosmos, it all connects. And that connection? That's what makes me love astrophysics.